my friends. Welcome back to another video from our new series, which is machine learning tutorial with Python from scratch, right? In this series, as I told you, we want to implement the machine learning algorithm, the most popular ones at least, in Python from scratch. We want to do everything ourselves. So in a previous video, we started talking about the k-nearest neighbor, right? We explained the math and the theory, and then we implemented that in Python, and we saw that we are getting the exact same results as in scikit-learn k-nearest neighbor function. Cool. Now let's move on to the next topic, which is linear regression. We saw that in a previous series, which was like advanced topics in Python. We talked about linear regression, so you already know what that is, right? But we want to implement everything from scratch ourselves. Now, it means that we have to dive a bit deeper into that and see how it exactly works. So we were talking about it. We said that we're going to say something like our y values, like the predicted values, right? They're going to be like wx plus a bias, right? W is the slope or the coefficient, and b was the intercept, right? And then we said that we want to find the best values, which is like the best W and B values that minimize the error. And then we said that like there is a lot of, different approaches out there, like different error metrics. One of the most popular one was the MSE or mean square, right? We said that for MSE, right, that's obviously a function of the weight. It also is called weight as well, or slope or coefficient, whatever you want, and know the bias, right? And then we said that if you have, for example, n samples, that would be 1 over n because it's mean, which is like the average value, and then squared error, right? So we have, if you want to calculate the mean, we need a sigma, and I'm just gonna say I equals 1 to n, right? And then the squared error, we have to calculate error. What's the error? Error is the actual value, right? In brackets, is the actual value minus the predicted value. And what is the predicted value? It's going to be wxi plus b. So that's y. And this is the error, and we're going to square that, right? Now, we want to minimize minimum score error, right? We want to have the least amount of error. How do we do that? We have to calculate the gradient of the MSE based on W and B, right? You remember, like if you had a function like this, right? If we wanted to find the minimum, then we had to be like, okay, let's say for example, we want to find the minimum is here, and this is like where the derivative is 0, like the gradient is 0. That's exactly what we're going to do here. We want to calculate the gradient of MSE with respect to W and B. And that's where the MSE happens, right? The minimum MSE happens. So if I define that and be like df dw, right? And I'm just, for simplicity, I'm just going to call that dw. That's equal 1 over n, right? This is simple math. So this was the main equation up here. And now I want to calculate the derivative. So it's going to be this, right? And then we have the sigma. And then, well, obviously, nothing is going to change. This is from 1 to n. And then if we do the gradient with respect to W here, we're going to get minus 2xi, right? Minus 2xi times yi minus wxi plus b. This is supposed to be b, right? This is what we're getting. And if we do the same thing, I'm just going to do it up here. Sorry, it's not the cleanest, but you understand what I'm saying. So df over db, that would be 1 over n. and then we have the sigma minus 2 yi minus wxi plus b. So this is the equation, right? So we need these, right? We need to minimize this. So how it actually works is that now it's an iterative method, right? So if I have this curve in here, right, and I want to find the minimum, and I'm saying, okay, I'm at this point, and I calculate the slope or the gradient, and I'm saying, okay, I'm here. Now the next step, I want to go to here, right? And then like here, and then here, and then here, until I finally make it down here, right? So there is like a parameter here that we call this a learning rate, right? If you have like a small learning rate, it means that before jumping to that, let me do this. So I'm just going to be like W equals the previous W minus alpha, which is our learning rate, times like dW, for example, right? And this alpha in here, that's our learning rate. If you like, this is like a small number, it takes forever for you. Like you need a lot of iterations to get down here. And if it's a large number, then you may actually like pass this. Like what may happen is that like a jump from here to here, and then from here to here, and then like from here to here, and then here to here. So you may actually never converge. So you need to find like a really good alpha value or learning rate value. So with this in mind, let's actually jump into our Python and start coding. Just remember these two equations because we're going to need this one and this one. We can come back to that later if we wanted to, but like this is, as I said, very simple math, right? Nothing too crazy here. Okay, so that's about it. And let's actually start coding here. Let me clear this. And to start, as we did in the previous example, we're going to see first how the linear regression model from the scikit-learn works, right? So I'm just going to go import numpy as np. That's the first thing I need to do. Import matplotlib.pyplot parplot as plot. And then I'm just going to go from scikit-learn, import datasets, also from scikit-learn dot linear model, scikit-learn the linear model, import linear regression. We've seen this before. Nothing new here so far. And from scikit-learn dot model selection, import train test split, right? So these are the libraries that we're importing. And as I said in the previous video, in order to be able to reproduce the results, we're just gonna go random.seed and set that to any value. Just set it to 0, but you don't have to. You can set it to any other value that you want. Let's get started. So I'm just gonna go x and y. That's equal data sets, right? But make regression. We want to create our own data set here, right? We've seen this before. And number of samples by default is 100. Let's change that to number of samples equals 200. And then number of features, I'm just going to set that to 1 for now. And let's add some noise to the data. If we don't add noise, actually, let me show you. If I go plt.scatter, right, x, well, x, we have to see the shape of x, right, Leah? Because it has the features in it. It's going to be an array with like 200 samples and 1 feature. So it's an array. So we have to reshape the array, right? So I'm just going to go reshape this to, we have 200 samples. So I'm just going to put 200 in here. right? Well, 1 and 200. And plot that against y and plot.show, right? And let's run that now. And we'll see that like we have here 200 samples, but like they're in a line, like it's going to be an exact line. We're going to get an accuracy of like 100%, right? That's what we need to add some noise here, right? I'm just going to go comma noise equal, I don't know, like 20 or 50, whatever, like principal 30. That's like the standard deviation of the noise that it adds there. And now if I plot the same thing again, you will see that it's not going to be an exact line anymore. And like we have like some scattered data here. Cool. So this is our data. Let's not worry about plotting the data for now. And then the next thing we need to use always, we're going to go x chain, x test. It's y chain and then y test. That equals chain test split of x and y with test size 0.2, right? And now let's see, like again, the regression model from Python. We define a regressor that's equal to linear regression. We create the object, right? We create the object here, and then we can go regressor that fit, right? We need x chain and obviously y chain. And then we can say, I don't know, like print if print, I'm just gonna say coefficients or coefs that's equal to regressor.coef, and do the same thing for the intercept. Just gonna go f intercept equals regressor.intercept, right? And to see how good of a model we have, one of the reviewers actually, one of you guys pointed out something in the previous video, and they said that you can actually use model.score, and we can actually do that here. We can just go print, and then we can say model accuracy is, and we want to get percentage, so 100 times, and regressor dot score, right? It basically returns the R2 score of the model. And so the good thing about it is that you don't really have to do the like calculate the predicted value and stuff like that. So you just need to provide the X test and the Y test. So it has the regressor. It knows how it's going to perform on the test values. And then it has you provide it with the expected values as well. So it calculates the model accuracy based on this score in here, which is the R2 score. So if I run that again, and this is what I'm going to get. It says the coefficient is 96.7%, which is like pretty good. The intercept is that, and model accuracy is like 92%. Cool. So this is working, and we expected it to work because we've worked this before. But now we want to actually define our own linear regression, right? So just like before, I'm going to define a class. I'm going to call it my linear regression, right? And again, as always, we're going to go define underscore init underscore. Don't worry about the autocomplete thingy self, obviously. And then I'm just going to give it a learning rate. By default, I want to go set it to 0.001. And like this is a pretty common value, or like even this. Based on the algorithm, like people come up with different values, but this is like pretty decent for linear regression. and then obviously number of iterations. I'm just gonna set that to 1,000, for example, for now. And when I call this, I'm just gonna go self.learning. Let's just like keep it short. Learning rate, that equals to learning rate. Self.number of iters. If the iterations that we want, that's obviously number of iter here. And what else do we need to do? We need to initialize this. This is the init, right? Like where we initialize things usually. We have the weights and we have the biases. So I'm just gonna go self dot weights. That's equal based on the number of features, the shape of weights may vary, right? And I don't know what that is just yet. So I'm just gonna go, I don't know, but they just set it to none, for example. And self.bias. I'm just gonna set that to none as well. I think it's good for the init function. Now let's have our fit function. It's gonna have obviously self because it's method of the class, and x and y, right? Let's close this. So in here, what we need to do, I'm just gonna go number of samples and number of features, right? That equals x.shape, right? We've seen this before, nothing crazy. If we have 200 samples with, I don't know, 2 features, for example, we're gonna see 200 here and 2 features here. We need this, I'll tell you why in a second. And I'm just gonna go self.weights, right? Now that we have the size, I'm gonna set it to all zeros, right? It can go numpy. We did import numpy, right? Yes, numpy. Numpy dot zeros, and how many zeros? I need number of features, right? A lot of people may actually want to set it to some random values, but for linear regression, it doesn't really matter. We can just start from zeros, and then I can go self.bias. That's just like one value. It's set to 0. I could have actually done that in init as well, but we can do it here as well. That doesn't really matter. And as I said, it's an iterative value, right? We want to repeat updating the weights and the bias value until like we get to a good point. That's like what this iteration here is for. So I'm just gonna go for I in range of how many do we have? It's self dot number of iters, right? I'm gonna say y pred the predicted value. What is it? It's x times w, or w times x, right? Because it's a numpy array, I'm just gonna go numpy dot dot. The dot is like basically the multiplication thing. You can actually read the documentation of numpy dot to see how it exactly works. And I'm just gonna give it x and self dot weights, right? And once we have that, then plus self dot bias. So far so good, nothing too crazy here. And now I need to calculate the gradient, right? I'm gonna go dw, that's equal, based on what we calculated, it's 2 over number of samples. See, number of samples calculated here in this function, so I don't really need to define it as like a self thing because I don't want to use this in the other methods of this function. So it should be good here. 2 over number of samples times, if you remember, it was x times y pred minus y, right? I can actually show you here quickly. 2 we brought 2 out. It's like xi times this. And if you look at it, like if you take this minus in here, that would be this minus this in here. And this is the predicted value, and this is the actual value. So it's xi times predicted value minus the actual value. So let's go back here and do that. So I'm just gonna go numpy dot dot, right? X, and it's gonna be y pred the value that we calculated up here, this minus the actual value, which is the y that is like the input to this function in here. And then we can do the same thing for updating the bias values. db equals t over number of samples, and then that times numpy dot. Well, there was no dot function, if you remember here. Like if I go here again, you see like there is no xi. It's like 2, we brought 2 out, and then like it's y pred minus y, and like there is a summation, right? The dot product here, it does the summation itself. Again, like you can read the documentation on that. So anyway, here I'm just gonna go y pred minus y, right? And I'm just gonna go self that weights, right? That's minus equal alpha, which is our learning rate, and that would be self the learning rate times w, and then we can have the same thing here for bias. So that's db. So far so good, and that's about it. So this is our fit function. So one point here, as you see, we never actually use the variable I, right? Which says for I in range this, but we never actually used y. So a good practice is to like go underscore here. Like this is one of the use cases of underscore in Python programming. It doesn't really matter. You can keep it as I, but it's good practice to, you know, be aware of these things. Anyway, now that we chain our model, what we need to do is to actually have the predict value. So I'm just going to go define predict, right? Obviously it has self, then it has some x values, because these would be the test values that we need. And that would be, we're gonna return, what are we returning here? It would be mp dot, it's basically the equation that we calculated, right? X and self dot weights. Now we have that plus self dot bias. So these are going to be the exact of the calculated value in the previous step. And then like it's because we want to compare the accuracy and the performance of our own linear regression method with that of scikit-learn, it's good practice to, you know, print the final values. Like after every calc, all the iterations are done in the previous step in the fit function, we can actually come here and say print coef, that's like self dot weights, right? And then I'm just going to call that our own models coef is that, and just copy that, bring it up here, and we can go intercept is self.bias. So it should be good. I think that's everything we need. And now we can actually see how it works. I can go regressor equals, and now I want to use my own class, like the class that I defined. So regressor is going to be an object from this class. Great. We can do the same thing. We can go regressor.fit with x train and y train. What's happening here? Y train. So we are chaining our model, and we can go y pred equals regressor.predict. That's the predict function that we had there. So we need to provide it with the x values. In this case, it's going to be the x test. Now we have the predicted values, right? So if I run this now, I should be able to, when I predict in here, we have the coefficients and the intercept as well. And then I know what Python returns, right? So if I go up here, I go SKlearn, intercept, and then SKlearn coefficients. So it should be good. Let me clear this. And if I run this in here, okay, it's going to error out, obviously. It says line 33. Let's see what's happening here. If I go to line 33, right? Well, it's here. It says, let me open it actually and close. Okay, in line 33 here, it says that np.x and like this. And what's the problem? It says shape 160 by 1 and 160 nothing, not aligned. One has one dimension, like dimension 1, and like the other is dimension 0. So we obviously are messing up something. We're doing the matrix multiplication or array multiplication using the numpy dot function, right? As you know, if you want to like multiply this and this, the second dimension needs to match. So it means that we have to transpose this matrix in here. So all I need to do is to go .t, which transposes the matrix for me. Yeah, that's good to note. And I clear this, and hopefully that fixes my problem. If I run that again now, it says scikit-learn coefficient is 96.7 and scikit-learn intercept is -3, and the model accuracy is 92, right? We expect to see something like that as well. And as you see, like our intercept is 83, which is close to 96, and like -2, which is like very close to -3.4. So you're getting there. We're doing it, but we don't exactly match. So what we can do is to actually increase the number of iterations here, right? Because as I said, it's an iterative process. So if we keep doing what we're doing, then we should probably like get some better results. So if I go to like 2000 iterations now, and we don't really need to print out the model accuracy anymore. So if I run that, it says, well, 96 is not going to change, -3.4 is not going to change, but now you're actually getting 95. You see, previously we were getting 83, but now we're like 95. I'm -314, which is like super close to 342. So we're getting there. We're closing, right? So what else can we do? We can actually go here and just say, okay, do that for like 5,000 times, right? See if that actually changes anything. And if I run that again, it says scikit-learn coefficient is 96.7 and we're like 96.69, which is like very cool. So we're basically matching. It's like -2.42, -3.419998. So we're super close, right? I think at this one we can say it's like good enough for us. And what else can we do here? We can, we tried it for like only one feature. I can increase the number of features and be like, you have 4 features, right? So that you see that it's going to work with any number of features. That's not like a limiting factor for us. If I run that, it says scikit-learn coefficients are these and our own coefficients are these. So 5.34, 0.436, which is close, 60.3, 60.29, which is close, 71.81, 78, and 41.96 and 41.96, right? And the intercept obviously is like also very close. If you're not happy with this, still like you can increase the number of iterations. It's gonna like slow down your model a bit, but again, it depends on what you want to do with this. So that's about it, and it should be good enough. And then like you can obviously plot the result that you have to see how it works. If I go here and be like plot plt.scatter, what did I call that thing? Okay, well, because of what we want to plot, right? We can go, I want to see X test and Y test, right? And I also want to see scatter of X test and Y pred, the predicted values, right? Plot that share. We just want to see, like, visually see how close we are. And if I run that now, you'll see this. So the orange dots are our model. It's a line. Like, as you see, it's like basically a line. And the blue dots are the actual values. So real close, like I would say it's like really good. And we saw the accuracy of the model. It was like 92%, if I'm not mistaken, or 96. I don't remember exactly the R2 score that we calculated. Anyway, so this is all for today. I really hope that you enjoyed the video, and don't forget to subscribe and like so you won't miss the next video that I upload. And thank you for watching me. Take care. Have a good one. Bye bye.